Hi, I'm Andrew, and today I'm going to present you our multi-explainable solution. So currently our solution is the fastest solution in the machine learning community. So this is a work I cooperated with Arash, who is the head of our AI research labs in MOTSI. In this session, I would first start to explain what is explainable AI and why do we need it. And then I'll start to introduce some of the self-explanatory models, which means that we don't even need tools to try to understand what the model is doing. They are directly explainable. And then I'm going to present some of those state-of-the-art solutions. So these solutions are able to explain complex models, such as deep neural nets. So they are LIME and the gradient attribution method. Finally, our main dish, our multi-solution, which has a fancy name called AXAI. And then I'll end the session with conclusion and Q&A. So first, why do we need explainable AI and what it is? So in real-world applications, there are a lot of situations when we have to fully rely on machine learning models, such as using an object detection model to try to track down license plates through millions of video frames. Or it could be in the financial sector when we are trying to find anomaly in huge financial databases. So people started to think that when we are fully relying on those machine learning models, we have to build trust among them. But how do we trust them? So people started to develop tools to understand what models are thinking. And that's really, really important. So this is called explainable AI. I would like to use two examples to show why explainable AI is useful. The first one comes from a paper visualizing and understanding neural models in NLP. So in this paper, the authors tried to compare three different models: the recurrent neural network, the LSTM model, and the bidirectional LSTM model. So the tasks of those models are to try to detect the polarity of movie reviews. So such as this one, I hate the movie, though the plot is interesting. It is pretty obvious for a human to think that this is a negative review. And all three models, they do think that this review is negative. The problem is that the authors try to understand why those models think that this movie review is negative. It turns out that in the first model, the recurrent neural network, it thinks that interesting is the key word that leads to negativeness. In LSTM, it turns out to be the word hate. But in bidirectional LSTM, this model tries to balance between hate and interesting, which is more like a human. So if I were the guy to select a model, which one would I trust? I would trust the last one. So explainable AI helps us to do model selection. Now, in the second example, in figure 2, we see an image of a husky that's classified as a wolf. So this example comes from the LIME paper. So the authors developed an explanation tool called LIME and used their explanation tool to explain why the model thinks that this is a wolf rather than a husky. It turns out that the explainable feature is the jaws. So what happens is that in this training data set, a lot of huskies and a lot of wolf images has the similar jaws. So when the model is trying to see whether this image is a husky or a wolf, it turns out that the model has a really hard time to try to differentiate the two. So it thinks that it's a wolf, and apparently it's not. So explainable AI at this point serves as a debugger because it debugs what's wrong in the model. So if I were to do the experiment, then I would add more images of huskies and wolves, but with different jaws so that the model could learn furthermore. In this slide, I would briefly talk about two examples that are self-explanatory. These are really simple models, such as the linear regression model and the decision tree model. For linear regression, this should be familiar to all of you. F of x is the output. The x's are the input features, and the beta coefficients are the weights. So basically, the beta coefficient actually means the rate of change of the output with respect to the input. So if I want to find the most important feature for the model, then I would definitely pick the feature that is multiplied with the largest beta coefficient. So this is for linear regression. Now we look at decision tree. This is also pretty simple. When a decision tree is constructed, we have to split the nodes. So when splitting, there's the change in information gain. So basically, we could try to find the most important feature by looking at the information gain. In this page and next page, I'm going to talk about two state-of-the-art solutions that is really reliable and stable. The first one is called LIME. It stands for Local Interpretable Model Agnostic Explanations. I won't go pretty deep in the theories of LIME, but basically what LIME does is that LIME tries to build an alternative model on top of a black box model. So let's say we have a cat image and we have a convolutional neural network, which is a black box model. What LIME does is that LIME perturbs that input, the cat image, into different inputs, the perturbed inputs, and then use these perturbed inputs to learn a new linear model. And since it's a linear model, like a linear regression model, it's self-explanatory. So now the beta coefficients are the explanations itself. So basically, this is what LIME does. And in summary, we could see the equation down there, which is what LIME does. It tries to optimize this equation. It tries to decrease the distance between the black box model and the alternative model, which is the explanation model. So the more close those two models are, the more accurate the explanations are. So now let's look at the second state-of-the-art solutions called the gradient-based attribution method. And this method is not something new, no matter it's in the computer vision community or the machine learning community. People call this the saliency map. Basically, what the saliency map does is that it extracts the gradients of the output with respect to the input and use these gradients as explanations. The intuition behind this is the linear regression case we have seen before. We could simply differentiate the output with respect to the input features, and then we could get the beta coefficients. And these beta coefficients are the explanations. So this is pretty simple. So let's look at an example. Figure 6, our input is an antelope, and we have a black box model. Just think of it as a convolutional neural network that tries to classify what animal it is in this image. The saliency map or the sensitivity map is shown beside it. One can see that there are a lot of dots clustering around the antelope. So this definitely means that the model has an idea where the antelope is, but this does not really show why it's an antelope. Moreover, as you see the sensitivity map, it's pretty noisy. There are dots in the background. So when people are using saliency maps, some people have to develop thresholds that filter out those background dots, because those dots in the background means that the background has some information for the model to decide whether this is an antelope. However, is this information really important? What if we change the background? The model should still think that this image is an antelope. So people have to deal with this. The second problem is that gradients are noisy. I'm going to further explain what do I mean. in terms of noisy in the next slide. But basically, in short, these noisiness comes from the discontinuities and the sharpness of nonlinear activation functions, such as the max function, such as the relu function. And also there are something in the convolutional layers that could lead to noisy gradients. So let's first focus on figure 9. As you see, this is a relu function centered at 0, which has a slope of 0 in the negative range and a slope of 1 in the positive range. So let's say I fed a terrapin, an image of a terrapin like the one in figure 7 inside a black box model. It turns out that one of the pixels, let's say one of the pixels in the eyes of this terrapin is the gray point in figure 9. So now the slope is 0, which means that this pixel or this feature is not important at all. The problem is that if you have the same image, but with a brighter version, just like a brighter terrapin image, then this gray point would be slightly pushed towards the right-hand side to the red dot. So what happens here is that before the slope is 0 at the gray point, now suddenly the slope is 1. So it jumps, the gradient jumps from 0 to 1, which means that before this feature, this pixel is not important at all. However, after you give it like a brighter version of the original image, this feature became so important. So this creates some confusions and people are trying to solve it. So I present here like 2 different methods which come from the paper references down below. One of them is called integrated gradients and the other is called smooth grad. Both of the 2 solutions try to deal with noisy gradients. So for integrated gradients, what they are doing is that they would pick the original image and a base image, and then interpolate multiple images between them. For each interpolated image, they extract gradients. And then, so now you have a lot of gradients because you have a lot of different interpolated images between the original one and a black image. And then you average them. So I want to illustrate what this happens. So in figure 9, as you see, what integrated gradients do is that they have additional dots between the gray dot and the red dot. So when you average those, you would have a value that's not 0 or not 1, but something in between. So that solves the problem. Another solution is called smooth grad. So smooth grad does something really similar, but in a completely different way. What smooth grad does is actually pretty intuitive. They randomly add Gaussian noise on the original image. So it's like it's perturbing the image. So if you look at figure 9, what smooth grad is doing is that it continually pushes this gray point on the right or on the left and create a lot of different versions of it. And then they average all of them. So since they average all of them, we also solve the noisy gradient problem. And I want to mention that why I spend so much time talking about noisy gradients, because our MODSI solution also deals with this kind of problem. And we could successfully overcome this problem by using iterative attacks. And that's what I'm going to tell you in the next slide. So now I would like to present you our MODSI solution called AXAI. So AXAI stands for Adversarial Explanations for AI. And this is a work between myself and the head of our AI research labs, Arash. Our initial idea is that in adversarial attacks, what an attack does is that we attack the model, and then the model would generate adversarial noise on the image. So some features, some pixels on the image would be manipulated or perturbed, so that when feeding this perturbed image inside the model could not recognize it at all. This leads us to think that we want to try to extract those manipulated pixels, because these pixels must be really important, or else why, when manipulating them, the model could not recognize it at all. So basically our idea is that we attack the model, we extract the attacks, and then we have to do some processing. So then we could generate explanations. And I'm going to explain the whole workflow in the following slides. So first, before talking about the workflow, I want to first introduce the attack we use in our AXAI solution. The attack we use is called projected gradient descent. It has a formula like this, where X is the input image, the original image, and X star is the perturbed image. So everything on the right-hand side of this plus sign is the adversarial noise. The Y is the true label, X is the input, theta is the model, and L is the loss function. So what we're doing here is that we are taking the L2 norm of the gradient of the loss with respect to the input. And this noise is multiplied by a small number, an epsilon coefficient. And this is the attack we would like to extract. So now let's talk about the whole workflow for AXAI. I know that simply look at the workflow, it might not be so understandable. So I also provided figure 11, which is a real case for illustration. So I'll first go through figure 10 and then to figure 11. So first, let's focus on figure 10. If given an original image and a model, the first step we do is to do a PGD attack, just like what I mentioned in the previous slide. After attacking the model, we extract the attacks. So we call those attacks the attack magnitude in this workflow. And then we are doing some filterings. And first, bear with me right now, because this filtering process is one of the major works in our paper. So I'm going to elaborate that in the next slide, but not now. So at the same time, we also need to segment our image into image segments. So we used a tool called the Quick Shift Image Segmentation tool. So this tool simply segments the original image into different pieces. And then finally, we arrive the mapping process. So what happens here is that we have the image segments right now, and we also have the filtered attacks, and we stack them together. And then we count the frequencies of the attacks on each image segment. It would be way much more clear when we go through figure 11. But so after we do the mappings, we simply pick the top segments that has the top frequencies of attacks, and we use that as explanations. So now let's look at figure 11. This is a case of a cat fed in a model called ResNet34. So first, we attack the model, and then we extract the attacks. So these attacks would look like figure 11C. If you see the color bar, those attacks are definitely not human recognizable, but these are the attacks. So as I mentioned that we have to filter out some parts of the attacks. So as you see in figure 11B, we have two red straight lines. These are the thresholds. So we throw away all the attacks in the middle, and we save the attacks that's not in the threshold. So basically figure B is a histogram of attacks, which I would explain in the following slides. So now we also mentioned that we have to segment the original image into image segments, and this is in figure 11D. Finally, after we go through figure 11A, B, C, and D, we do the mappings. This mapping process stacks figure 11C on top of figure 11D. So now you could imagine that there are attacks all over these segments. So basically we start to count the attacks on those image segments, and we pick maybe the top 3, the top 2, is up to the user. So in this case, we simply picked the top 3 segments that has a lot of attacks on it. So we have the explanations, which is figure 11E. This explanation shows that the ears and the nose are the important features of this cat image, so that the model thinks that this cat image is a cat. One thing to mention is that from figure A to figure E, it seems to be a complex process. However, when operating on a single NVIDIA GPU, it only takes seconds. Depending on the size of the input image, it could be within seconds. So it's really, really fast. So later on, I would provide some benchmarks. So you could see how fast it is compared to other state-of-the-art explainable solutions. So in the previous slide, I've mentioned that we have a filtering process, which we throw away a lot of attacks of the attack distribution. So why do we do this? Because recall one of the examples in our previous slide. When we are explaining why the model thinks that an image is an envelope, we see the gradient map and we found that there are a lot of dots, a lot of gradients in the background, but these are actually noisy gradients. We don't need these, so we have to filter it out. So we're thinking to set a universal threshold on these attacks so that we could just throw them away. And based on the theory of adversarial attacks, when the attacks are large, it means that these features are important. So we need a large attack to change them. If the attacks are small, it means that these features being attacked with small amplitude are not important at all. So these are unimportant features. So definitely we want to filter out those small attacks. So we need to set the threshold so that all the attacks that are less than this threshold, we want to throw it away. But before doing this, we have to make sure something. We need to do some experiments and to see what the distributions of those attacks look like. So we have tested different data sets, different models, and different tasks, and we extract all the attack distributions of these models. I found something really interesting. If you look at the histograms of those attack distributions, they are they all look like a bell shape. But this is just visually, they look alike. We need statistical analysis to back us up, to prove that there's no significant differences between them. Once we have proved that, then we could simply draw 2 lines like the threshold and just throw away everything that's smaller than some threshold. So what we did is that we did several hypothesis tests on those distributions, including a Mann-Whitney U test, including Fisher-Pearson skewness test. And we also compared the quantiles using quantile plots. And it turns out that we have an interesting conclusion. We found that all the distributions belong to a beta distribution within a certain range of parameters. And we are really excited because now we have proved that those distributions do not significantly differ with each other. So we could easily build thresholds on these distributions and throw away everything that is below this threshold. So now there's another problem right here. How do we set the value of this threshold? So we did an additional experiment. We re-attacked all the models with the same attacks, but only using the first n% largest attack values. If you look at figure B, that means that we are only using the tails of this bell curve to re-attack the model and to see whether the model could identify or could not identify the input image. It turns out that simply using 30% of the largest attack, we could successfully fool the model, which means that only 30%, this is on average, so only 30% of the features are important to the model. Other than this, these are noisy explanations, noisy features. So that's why we need a filtering process to filter out all of these unimportant features by setting thresholds on it. So finally, I'll talk about benchmarking. Benchmarking an explainable solution is not easy. So our thought is that why don't we evaluate our explainable model among those state-of-the-art solutions, such as LIME, such as SHAP, a global method, and see that there's some huge differences between them. And it turns out that our model works pretty well. It has accurate results when comparing to those other solutions. We could see in figure 13, we have an example of a gas station, a gas pump. Another example of a praying mantis, and another with friends. All of those explanation results align with each other. And as I mentioned before, our AXAI solution is currently the fastest solution in the world. It only takes a few seconds on the compared to LIME and SHAP. These two solutions would take around 100 to 120 seconds to process the explanation results if the input is an image in ImageNet. So definitely, if we work on a single GPU or multiple GPUs, it's way more faster. It could be within 1 second. So after benchmarking, I want to show some examples, not only on image classification, but also on other applications, which I will show in the next slide. So let's first look at some examples on image classifiers. So in figure 14 and figure 15, we have different combinations of data sets and models. For figure 14, it's a VGG16 image classification model trained on CFAR 100 dataset. And for figure 15, it's AXAI image classifier trained on CFAR 10. As you can see the results, these are really good results. So our AXAI solution not only works on image classifiers, it also works on object detection, V3. It also works on audio recognition and NLP models. So let me explain those. In figure 16, it's the explanation results of a speech recognition model called Lynette. And those data sets come from the speech commands data set, which includes a lot of audio files with a human pronouncing short words like right, tree, go, stop, something like that. So the model has to eat spectrograms. So definitely the explanation results would be shown with spectrograms. So we could see these two examples, right and 3. And we could see our AXAI solution provides some pieces of explanations at the first few seconds of right. And there's a reason behind this, because there is another label called 8 in the data set. So for the model to differentiate right and 8, the difference is the beginning, the R. So that's why our AXAI solution shows there's the explanation results are the R sound. In figure 17, I show 2 examples of explanation results on a YOLO V3 object detection model. The task of this model is definitely to identify the bounding boxes of those buildings. And if you look at the explanation results, it is clear that it shows all the buildings inside the image. So it performs pretty well. Finally, we go to the NLP task, which is a text classification task. And the task of this model is try to decide the polarity, whether this IMDb movie review is positive or negative. So the first one is, it's a glorified sitcom and alone or funny on that. So it's clear that our results shows that the word unfunny is critical for the model to decide whether this movie review is positive or negative. In another example, a work of astonishing delicacy and force. It is also shown that the word astonishing is the key word for the model to decide it's a good review or a bad review. This is really similar to what a human thinks. So finally, I'm going to talk about 3 nice properties. So this is like a conclusion of our AXAI model. We have 3 nice properties that is worthy to talk about. The first property is called interpretability. So an explanation has to be human readable. What that means. If I give you an image of an antelope and you give me a gradient map with a lot of dots around this antelope, well, this is not really clear to me because the dots are all over around. It doesn't really show the antelope in the image. So our AXAI solution actually uses image segments to show the explanations. So in the case of an image of an antelope, we would directly show the head or the tails or the body of the antelope, rather than just giving you a lot of dots on it to tell you that this is the explanation. The second property is called local attribution. So this is a property that is almost the same as what it is stated in LIME. So our method is a local method. With a given input, we provide explanations. We don't need to access the whole training data set. An input with an explanation, that's all. It's local attribution. And the third one is completeness. So what completeness is that our AXAI model solves the noisy gradient problem that I've mentioned when I'm introducing smooth grad and integrated gradients. We are able to remove those noisy gradients by using the attack we use called PGD, the projected gradient attack. Because this is an iterative attack. So actually what we are doing is that we are continually attacking the model and extracting the attacks, and we sum them up. So this is like the averaging process in integrated gradients or smooth grad. We basically implicitly solve the noisy gradient problem, so we could create clean explanations. So finally, I want to end this session with this graph. So this graph shows the publication of papers that is related to explainable AI. Before 2016, people don't really care about understanding why a model could do such a decision or how the model do decisions. People only pursue accuracy. We built large, complex models and train on large data sets. And we want to increase our accuracy, want to increase the performance. But then in 2016, people started to get aware of trust AI or AI trust. It's important to trust our AI models because there are a lot of decisions that are purely based on those machine learning models. So it's really important to understand what a model is thinking. So that's why in our Mozzie labs, that's something we are working on really hard to tell people that what our models are working on. So to be confident with them, this part. Thanks for listening to my presentation. And I encourage you to visit our Mozzie website. There's more information and resource on our website. Thanks.